Okay, so in this video, we will be looking at the second half of chapter 6, which is the hyperbolic chapter, but I focused on just the things to do with calculus here. This one follows on really nicely from chapter 3, methods in calculus, and often when I teach it, I do it in that way as well. What I always say in these videos is it's not possible for these chapter summaries to cover all of the possible ways that examiners can assess the topic. So please make sure that you are also looking at lots of different exam questions. And in particular, this video is going to be focusing a lot on the skills of this. These topics can be asked alongside lots of other things in further maths. Maybe things like the mean value of a function, maybe things like improper integrals, maybe volumes of revolution. So we're really just looking at the skills for hyperbolic calculus that should set you up to answer some other questions. So we're going to start off by looking at some things to do with differentiation, and I want to kind of look at some of these things here. Now, the ones that I've included are all ones that are actually in the formula booklet. These ones are not in the formula booklet, and so far for edXL, they haven't really assessed them, but I thought it would be useful for us to just kind of have them here in case they were to ever come up, because they're not that difficult to remember. So these ones are all positive for the standard hyperbolic trigonometric functions that we have here. To memorize these ones, they are just the same that they are with trigonometry, but they are all just going to be negative, okay? And I'll give you another tip of remembering them in just a second. So they're all going to have negatives. When we do sec, normally, sec goes to sec x tan x. So this will go to sec x tan x, if I can squeeze it in, and it will be negative. Cosec normally goes to minus cosec cot, so it's just going to still be the same. It's going to be a minus cosec x coth x, so that's negative. And then coth x normally goes to minus cosec squared x, so this one is just going to stay as the minus cosec squared x, like this. So one of the ways of remembering it is that they are all negative. The other way of remembering it is which are the ones that have changed from their trigonometric one. Now cos normally goes to minus sign, but here it has gone to shine. This one is the same as its normal trig. This 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 is the only one that is different in the bottom half. So the two that are different are cosh and sech, and cosh and sech are obviously related to each other because sech is the reciprocal of cosh that we've got there. So two ways of remembering it. The ones with the stars are different, or you can just remember that all three of these have the negative sign at the beginning. And of course, we have these three that are down here. They're in the formula booklet. I don't bother memorizing these myself because they're all too similar looking to each other. So I always have the formula booklet open when I'm doing any of these kinds of questions. And of course, when we do this kind of differentiation, we just need to make sure that we can do the chain rule, the product rule, all of that kind of stuff. So again, it's really just practicing some skills that we've got here. So this first one that we're going to do, the r than, the inverse than of the square root of x. So we're going to be using this form that's down here. That's 1 over 1 minus x squared. But of course, there is going to be a chain rule with this. So when we differentiate it, we would expect it to go to 1 over 1 minus the thing in the brackets being squared, but we also have to multiply it by the derivative of this thing that I was saying was in the brackets, and the derivative of that, this is x to the half. I will pull the power down and I will reduce the power by 1 like this, so that what we end up with is 1 over 1 minus x, because the square root of x squared is x, and this is going to be multiplying by 1 over 2 root x, so that we can write this simply as 1 over 2 root x brackets 1 minus x for this thing that we've got here, okay? So chain rule, differentiate as you'd expect, multiplied by the derivative of the thing that was inside the function. Now this is a much more challenging chain rule that we've got here, because not only do we have a 2x to the 4 inside the function, we also have that it is being cubed. So this should feel very familiar with like differentiation that we would have done probably in normal maths as well for this. So it's further maths. We should be able to handle this. Sometimes writing it like this can make things a little bit easier to process of what's going on, that we've got the whole thing being cubed. So we've got something being cubed. I'm going to pull the power down. I'm going to reduce the power by 1. And then I need to multiply by the derivative of this inside thing. Well, cosh of 2x to the 4 is going to go to a sine of 2x to the 4, but there's that 2x to the 4 inside the function as well. So I also need to multiply by the derivative of this, which is going to be an 8x cubed. So there is also going to be an 8x cubed, meaning that the final answer for this, the 3 and the 8 gives us the 24. We have the x cubed. We have the cosh squared, 2x to the 4. and we also have the sine 2x to the 4. I don't really see them asking a question that's like this. Again, I said this is more of like a skills kind of summary rather than something that we would see in an exam question. Okay, here we've got something with a product rule, and also there's going to be a bit of a chain rule because of the x squared and the 2x here. So I'm going to keep this to the side so I can actually see what's going on with the formula booklet for this. I'm going to start off by differentiating the r cosh of x squared. So that is going to go to 1 over the square root of, that's going to be x squared squared, so it's going to be x to the 4 minus 1, and it needs to get multiplied by the derivative of x squared, and the derivative of x squared is going to be 2x. And then I'm also going to keep the second part, which is the sine 2x. And then for the second part of the product rule, I will have the r cosh of the x squared multiplied by the derivative of sine 2x. Well, that's just going to go to a 2 cosh 2x. So not looking particularly neat here, but I think it's going to be a 2x sine 2x over the square root of x to the 4 minus 1 plus a 2 r cosh x squared multiplied by a cosh 2x. Okay, kind of strange looking. I can't really see them asking something like that, but just to remind you, we might need to use the product rule. And then here we have an example of a chain rule for this. So we have tan of sine of x. Okay, let's put a little line there to make sure I'm not going to mix these questions up. So the inside function is the sine x. So I've got a tan of something. Well, I know that tan goes to sec squared. So this is going to go to a sec squared of the same thing, which is the sine x, and it needs to get multiplied by the derivative of sine x, which is cosh x. Now, you might think to yourself, oh, we have like a sec and a cosh, can they cancel? Well, they can't, because this sec is with the input. The argument is sine x, whereas here the argument is x. They don't have the same argument. So we cannot simplify them, so it's just going to be a cosh x sec squared of sine x. I mean, this just looks like complete jargon, doesn't it? And then this one, I've left some space because we might try it in two different ways, okay? One of the ways will just be going up and doing the product rule. So if I differentiate this, I will differentiate the first part and keep the second part. And then I will keep the first part and differentiate the second part, and cosh will just go to sine like this. So we have e to the x cosh x plus e to the x sine x. Or an alternative method for this might be to use exponentials. So if y is equal to e to the x cosh x, again, let me just kind of box off what we're doing here. Cosh x is a half. Tell you what, let's just put that half right to the front of this so that we have the other way of doing this. We have the half, the e to the x, and then we have the e to the x plus e to the minus x. When we expand these brackets, that is a half e to the 2x plus a half. So that's what y is equal to. If I differentiate this, I get that dy by dx is equal to, when I differentiate this, the 2 will come down, so we just get e to the 2x, and this part completely disappears that we've got here. So, without even needing to do any further calculation, I know that this thing must be the same as this thing. So if you want to try that out and double check, you can use your definitions of cosh x and sine x, do all the expanding over here, and you'll probably see, well, not probably see, you're going to definitely see it comes out as the same as e to the 2x. So if you want to check that in your own time, go ahead and look at that. So I just wanted to show you, sometimes exponentials can be useful, sometimes keeping it in its hyperbolic form is good as well. Okay, then we're going to look at some things to do with integration techniques. Now, I have not stated the obvious, that if you want to integrate sine, it goes to cosh. If you want to integrate sec squared, it goes to tan, etc. You've got to use the formula book in a creative kind of way. I don't want to kind of like add these extra things in. Use this page to help you go in reverse. But pretty much actually integrating these things should feel quite similar to the trigonometric stuff. So it should feel quite similar to some of the techniques from normal maths. So I've got 4 here. Lots of different things you might need to use for this. Think to yourself, what is going to be the approach that we will use for this first question? Well, I'm hoping you're able to tell me that to integrate this thing, you should see that we've got this cosh squared 2x here, and we've got this sine 2x. We've got this sine 2x, which seems to have come there from a result of some differentiation of cosh cubed 2x. So I think my answer is going to be something to do with a cosh cubed of 2x. And what you can do is check this. So if I differentiate the cosh cubed 2x, I will pull the power down, I will reduce the power by 1, and then I will multiply by the derivative of cosh 2x, which is going to be 2 sine 2x. So we've nearly got the thing that we were aiming for. We have the cosh squared 2x, the sine 2x, but we have this extra 3 and the 2, the extra 6 here, which means we're going to need to add in this extra 1/6 at the beginning. And of course, we need the plus c for this as well. If you want to check that this works when you differentiate it, there will be an extra 6th at the beginning, which then means we return to the thing that we were looking for. So this was an example of the reverse chain rule. Now, how would you normally integrate this kind of thing in regular maths? What would you do to integrate a sine squared function? Well, when we integrate a sine squared function, we have to use the rearranged double angle formula for cos. What we normally do is we would say that sine squared theta is going to be equal to a half minus a half cos 2 theta. That's what we typically do when we're trying to integrate sine squared theta. I knew something was going to go wrong when I did that. So what I'm going to do is I'm going to try and adapt this formula, and we have to adapt this formula using Osborne's rule. So if I was going to adapt this, this would become a minus sine squared x, or whatever it's going to be. In this case, we've got it with an x over 2. I'll just do it with theta for now. And then this is going to stay as a half. This is going to stay as minus a half cos 2 theta. So that negating, because of Osborne's rule, we've got this sine squared being there. If I change this so that it's just sine squared theta, I'm going to multiply by minus 1. You would have a minus a half and a plus a half cos 2 theta. So I'll write it as a half cos 2 theta minus a half. So this means we can now rewrite this. Instead of it being sine squared x over 2, using this identity at the bottom, we're going to be integrating instead a half cos of, well, it's not going to be 2x because the angle is x over 2, like the theta is the x over 2. The angle is going to double, so it's just going to be an x there. So it's going to be minus, see, I've written something wrong, haven't I? This shouldn't have said cos in these places. Did you notice this before I did? They should have, of course, said cosh 2 theta because we were putting it into hyperbolics. So I apologize if I didn't show you that before. So it should be a cosh, not a cos, but a cosh. We're going to double the angle from an x over 2 to just an x for this part. So there's going to be a half cosh x minus a half dx. And now that I've got it written in that form, I can just do the very easy integration. This is going to be a sine because sine goes to cosh. So it's going to be a half sine x minus a half x plus c. Okay, now we have a cosh cubed x. Unfortunately, there is no sine in front of it. If there was a sine in front of it, we could say it's going to be something like a quarter cosh to the power of 4. So we're going to try and use some other techniques for this. I think a sensible thing when you have this is to split it into a cosh and then a cosh squared, okay? You will start to get used to these things the more you see it. So I'm going to write this as a cosh x and a cosh squared x dx. And then I'm going to remind myself of the identity for cos squared, so I can use Osborne's rule to change it into the hyperbolic version. So I know that cos squared x is 1 minus sine squared x, which means that cosh squared x would be equal to 1 plus sine squared x. I remember to change them all to hyperbolics for this one. So I can replace this cosh squared with a 1 plus sine squared for this next line that we have. Let's just kind of box off that little bit that we were doing so it doesn't get in the way. So we have a cosh x, and that's going to get multiplied by a 1 plus sine squared x dx. The reason I wanted to do this is because I'll now have a cosh with a sine squared, which means we can do a reverse chain rule, and a cosh with a 1, which is obviously something that's very straightforward to integrate. So we have a cosh x plus a cosh x sine squared x dx. And that's pretty straightforward to do. Sine is going to go to cosh, that's going to be a sine. And then this one, very similar to this question we did at the top where we had the cosh squared and it went to a cosh cubed. We have a sine squared. Because of the cosh that's there, we can just say this is going to be done by a sine cubed x. Now, if you were to differentiate this part, you would pull the power down, you would reduce the power by 1, and you would multiply by the derivative of sine, which is cosh. So we've almost got the thing we're looking for, apart from there's this extra 3. So of course, we're going to need to add in that third at the beginning to counter that. So none of this feels that further mathsy to me. Obviously, it's very hard integration, and obviously there's hyperbolic things in here. But if these were all trigonometric, and I just said to you, how do you integrate these things? You would just figure out how to do it in normal maths. It would be a very challenging question, but the integration techniques are the same stuff that's from normal maths at this stage. This is probably the only one where I would say, obviously it's going to be very different because you do need to know about hyperbolic functions for this. Because of the presence of this e to the x here, I think it makes sense to try and write the sine function in its exponential form. It just feels like it's going to be a natural way to do this integration question, okay? So we're going to have the half from the sine 2x. We're then going to have the e to the x, and then we'll have the e to the 2x minus the e to the minus 2x. Just to clarify what I was saying, the sine 2x is the half with this part here. There's the extra e to the x that there was before. And now that it's written in exponential form, I actually think this should be pretty straightforward once we expand the brackets. It's just some really typical kind of exponential functions. So when we expand the brackets, we get a half e to the 3x, and then we get a minus a half e to the minus x dx. And so this is still going to be an e to the 3x, but because of this extra 3, I have to counter that, so that instead of it being a half, it becomes a sixth. A sixth times by 3 is a half. And then because of the minus in this bracket, I think it's going to be a half e to the minus x, but there will be a plus here. So when this minus x, when this minus gets pulled down in the differentiation, we have a negative here instead. And of course, we have a plus c for this bit that we've got as well. Okay, so this is, again, feeling quite familiar with some of the things that you should see from trigonometry, but instead we're now looking at some things to do with hyperbolic functions instead. Next up, we look at integration using the standard formulae. So, of course, I'm not talking about integrating these things in reverse, but I'm now talking about things that look like this instead. And these, again, are standard formulae that are in the formula booklet that we have. Okay, now I've included these ones already that were from sort of the previous methods in calculus chapter. The ones I've put in bold are the new ones that we have got here. And I sort of said that we'll be learning something later in chapter 6 that kind of completes the puzzle of that page of the formula booklet. I've also included these two that are down here as well. I think one of these was covered in the previous chapter summary for chapter 3 that we've got here. So very, very useful. I always have this page open as soon as I come across any kind of integration like this. And I talked about this in the methods in calculus chapter about, it doesn't tell you this in the formula booklet, but if you do need to use a substitution for something that looks like this column here gives you a clue about what that substitution might look like. So if you ever have any kind of substitution question where you have the square root of x squared minus a squared, this is going to be the substitution that you use. We can see there's a cosh here, and it's going to be an a cosh u. They always have the a in the front, and basically you can see which trig function or which hyperbolic trig function that you're going to use for a substitution. Now, the example that I'm going to do is I'm actually going to prove this one down here. I'm going to prove that the integral of 1 over a squared plus x squared integrates to r sine x over a, and I will use this substitution here. If, however, it wasn't something that was like a 1 over a squared plus x squared, if it just had this kind of function down here, this is typically going to be the kind of substitution that we use, and you'll see why when we go through this example, why that does something quite neat for this. And it's all to do with these sort of Pythagorean trigonometric identities for this kind of stuff, which all must sound like complete jargon, unless you're a further math student, and hopefully you kind of know some of the things that we're talking about here. So I'm going to show by using a suitable substitution that this thing integrates to this thing. If they didn't have that it was equal to this, we could look at the formula book and we could kind of cheat it and be like, okay, well, it's going to an r sine x over a. That's telling me the substitution that I will use is this one, okay? Looking at the connections between these things here. So we will start off with, where shall I do some of this work? I'll do it over here. We're going to use the substitution that x is going to be equal to r, I've even written it wrong, x is equal to a sine u. Now, I know at some point I'm going to need this dx, so I'm going to differentiate it. So dx du is going to be a cosh u, meaning that dx is equal to a cosh u du. And I'm going to try and build up now this a squared plus x squared thing. So if I do my a squared plus x squared, I will have a squared plus the x squared part is a squared sine squared u. Factorising, this is a squared 1 plus sine squared. Now, you should know that 1 plus sine squared is cosh squared. And I actually think we did that somewhere earlier on, didn't we? We said that cosh squared is 1 plus sine squared. So you need to recognise that this is why this one is going to work. So this is now saying that it is a squared cosh squared u. So that's what a squared plus x squared is, meaning, because I'm trying to build up what the square root of a squared plus x squared is just going to be my a cosh u. So I think I'm pretty much ready to go straight in with the substitution over here. So when I do the integration, it will be the integration of 1 over the square root of a squared plus x squared. So that is this part. This part here is going to be this. And then my dx part is going to be this. Okay. It's going to be 1 over a cosh u. I'm going to multiply it by dx, which is going to be a cosh u du. So the a cosh u's cancel, so we're just going to be integrating 1 with respect to u. When I integrate 1 with respect to u, we just get u plus c. So all I need to do now is find out what u is equal to. Well, if x is equal to a sine u, I just need to make u the subject of this. So that is x over a is sine u. So u is the inverse sine of x over a, which means I can finish this off by putting this u that we've got here in this place, so that we have r sine of x over a plus c, which is the thing that we were trying to prove that we've got here. Okay, so the clue is always in the formula booklet. It is always just going to be a trig function or a hyperbolic trig function with an a in the front, and you can tell from the formula booklet which one of those things that it's going to be. And the reason why this works is because when you have a squared plus x squared, you get this a squared plus a squared sine squared u, this thing that's here, which simplifies down to something really neat. This is a kind of version that will work for an a squared cosh squared u minus a squared. It gives you sine squared. All of these things simplify to something really nicely. If you are ever asked to prove these two at the bottom, you can just use partial fractions by factorising this denominator and factorising this denominator, and it's pretty straightforward with how you do those ones that you've got. And then the last thing I was going to say is that these two can also be written in logarithmic form, because we know from the previous chapter summary from chapter 6a, r cosh and r sine obviously have logarithmic forms as well. So lots of these things can be expressed in logarithmic form. Okay. Now let's actually use the formula booklet if we were going to try and evaluate this question. I've deliberately done it without limits so that we don't spend a lifetime doing this question. And the aim in this is to try and make the denominator look like something that is similar to one of these. And I think the one it's looking most similar to, with this 4x squared minus 18, well, I think it's this one, right? We have an x squared minus a squared. So I'm expecting to see some r cosh stuff here. But the x squared, it's by itself. So I need to first of all manipulate this so the x squared is by itself. I will do that by factorising on the denominator a 4 out. So I'll take out a root 4, which will leave me with an x squared and an 18 divided by 4, which is a 9 over 2. So we get a minus 9 over 2 dx. I'm going to take that root 4 out to the front. So root 4 is 2, so it's a 1 over 2. And then we have a 3x minus 1 over an x squared minus 9 over 2 dx. Now, if you've watched my previous methods in calculus chapter summary, you'll know the best way to deal with this is to split that numerator so that we now have two separate fractions. We have a 3x over the square roots of x squared minus 9 over 2, and a minus 1 over the square root of x squared minus 9 over 2, like this. Now we've got something that looks just like the formula booklet run. We have even got it with a 1 on the top, which makes it even easier. This part, I want you to think to yourself, how are we going to integrate that? And I'm going to give you a clue by rewriting it. So I'm going to rewrite this as a 3x, an x squared minus 9 over 2 to the power of minus a half. This one I'm not going to rewrite because it already looks like something very simple from the formula booklet. I mean, I say very simple. It is further maths after all. Nothing is simple. So I'm hoping you've figured out that for this first thing, we're going to be using the reverse chain rule. The derivative of x squared is 2x, so it's very similar to this part that we've got. So there's going to be a half. When I integrate this, I'm going to increase the power by by 1, right? So I will have an x squared minus 9 over 2 to the power of a half. If I just quickly do a quick bit differentiation on this somewhere else on my page, I will pull the power down, I will reduce the power by 1, and I will multiply by the derivative of this bracket, which is 2x. So the half and the 2 cancel, and we just have an x squared minus 9 over 2 to the minus a half. But I don't want it to be x squared minus 9 over 2 to the minus a half. I want it to be 3x, which means there needs to be the extra 3 that's in front of it. And then, for this part here, we can see that the formula, my x squared minus a squared, up at this place, a squared must be the second number. So a squared is 9 over 2, meaning that a is equal to 3 over root 2. And because later on in the formula we do x over a, I actually need to know what over a is, or the reciprocal of this is, which is why I often don't rationalize the denominator, because it means when I take this reciprocal, it's really easy just to write it as root 2 over 3. So, finishing off, it is going to be r cosh x over a. It is going to be a minus r cosh, and x over a will be using this, so it's this thing times by x, that is root 2 over 3x, close the brackets, plus c. I probably should have this half sort of expanded throughout, so I'll write it as a 3 over 2, x squared minus 9 over 2 to the half, minus a half r cosh of root 2 over 3x plus c. Very challenging stuff. This is where further maths is like, wow, you have to understand absolutely everything to be able to do these questions. Okay, we're going to do one last question here, which is a skill that involves some stuff to do with completing the square and potentially some substitution. But I will talk to you in a second about why we don't necessarily need to use the substitution in this question. And we'll get to that when we at that point in the question. Okay, so we are going to show that the integral of this thing is equal to this thing. Right, let's have a look at this technique of completing the square for this. Okay, I first of all don't like the fact that there's the 5 here. It looks very simple. I think if I just pull out that 5, I'm going to hopefully be able to get myself somewhere towards a form that looks like something of these ones. Well, it'll either look like this one, or this one, okay, because we've got the square root sign there. So maybe I'll do this immediately in the denominator, right? So we have between 3 and 5, 1 over. If I pull out a square root of 5, I would have for this part an x squared, taking out a factor of 5, a 2x, and a minus 3 like this, okay? Now, if I do this with a minus, there's a couple of different ways you could do this question, because this could factorize, okay? This is something that could factorize to an x minus 3 and an x plus 1, but then we've got it with a square root. I don't really think we can do partial fractions with this, which is why if we do completing the square on this, we will get a better form that will look more similar to something in the formula booklet. So over here, I'm going to do completing the square on my x squared minus 2x minus 3. So you know how to complete the square. This will be an x minus 1 squared. There'll be a minus 1 from the minus 1 part being squared, and the minus 3. So it's an x minus 1 squared minus 4. So these questions, they are demanding. So between 3 and 5, I'll put that 1 over root 5 outside the front, okay? This root 5 here is going to go to the front. The limits are 3 and 5. And written in its completed square form, we have x minus 1 squared minus 4 with respect to x. Now we've got it like this, right? This should look like something in the formula booklet. So it's a square root of an x squared minus something. It is the square root of an x squared minus something. Oh, it's this one. It looks like the inverse cosh. It's going to be an r cosh of x over a that we have here. But we don't have an x squared. We have something different. So we have an x minus 1 instead. So I've said completing the square can get our integral into a form that we can integrate. Great, this is now looking like something we can do. We can use the substitution of u equals x plus a. So we could use the substitution of u equals x minus 1, but it's not necessary. Instead, we can just adapt the formula. So in our formula where it says that it's going to go to an r cosh of x over a, it's just going to go to an x minus 1 over a in this case. You will see if you use the substitution, it doesn't change anything else because of the fact there is just a 1 in front of the x. So if it was of an ax plus b form, we have to be a bit careful because there's some scaling. Because it's just an x plus a, there's just some kind of shifting. We don't even need to use a substitution, even though they do it in the formula booklets. I've probably done an awful lot of waffle there. Let's just do the question and see what happens. So it's going to be a 1 over root 5. And then going in with the limits for this, we've said that it's going to be an r cosh of x over a. X in this case is no longer x, it's an x minus 1, because it's just that shift. We don't need to do any kind of substitution. And in this question, the a squared is 4, which means the a is 2. So it is r cosh of x over a, like this, x minus 1 over 2, between 3 and 5. So I will leave the 1 over root 5, and then I'm going to go in with the substitution of the 5 and 3 into this. So it is going to be the r cosh of 5 minus 1 over 2. So that's 4 over 2, which is 2. R cosh 2 minus r cosh of 3 minus 1 over 2. That's r cosh 1, like this. Now, r cosh 1 is simply equal to 0. So we have 1 over root 5 r cosh of 2. Now, I think the formula for this, that r cosh x is the ln of x plus the square root of x squared plus 1. Is that right, or is it x squared minus 1? I am going to just double check that. I'm pretty sure that it's x squared minus 1. Let me think to myself. Yeah, it's x squared minus 1. It's that. Should have had the formula booklet with me. I didn't. So this will be 1 over the square root of 5, the ln of 2 plus the square root of 2 squared minus 1. So it is 1 over root 5, ln of 2 plus root 3. And I think that's in the form that they wanted. So p is equal to 5, q is equal to 2, and r is equal to 3 for this question. Okay, that bit is in the formula booklet, and I've luckily been able to remember that from before. So completing the square can get it from some kind of quadratic with some square root into a form that you can do like this. The completing the square form should always work. But if you can factorize it and there's no square root sign, then obviously you can use a partial fractions approach. If there wasn't that square root sign and you did do the partial fractions approach for this question, you would still end up with the same thing. However, this one did have the root in, so it didn't work. My goodness, what a lot of stuff for hyperbolic calculus. The formula booklet is going to be such a companion for you when you do these kinds of questions. Do make sure that you use it as much as you possibly can do. As soon as I come across a question that looks like this, I always have it open on that page. Okay, guys, thanks for sticking with me through these chapter summaries. Hope to see you in another one sometime soon.